Hello everybody, welcome back to another Gregorious Maths video. Today I'll be doing another video on complex analysis. But the last video on complex analysis was a little crummy, it was a little snack. Now I'll get on to the big boy stuff, so to speak. Namely, today we're going to be doing an example of complex integration along a smooth path. And some of the theorems, like this one for example, I won't prove, but maybe in the next video if we hit 5 likes, I'll prove 2 theorems which will come up. So, first is the definition of a smooth path. So, a path gamma, sorry for my bad gamma, this is the best I could draw. A path gamma from the closed interval between A and B to the complex numbers, that's supposed to be that nice fancy C, is smooth if there exists gamma prime, so the derivative of gamma exists, which is continuous throughout the closed interval between A and B. So if the derivative is also continuous throughout the closed interval between A and B, then this path is smooth. Now, we're going to move on to the theorem. Hopefully you see what this means. I've done 2 videos where I've written out the definition of continuity, so you can refer back to those videos if you want. Okay, so what's our theorem? Our theorem is, for a continuous complex function, f, defined on a domain D, the smooth path, which is the way I gave the definition, the smooth path gamma from the closed interval between A and B to the domain so the integral along the smooth path of f equals the integral between A and B of f of gamma of t times gamma prime of t dt. And this might look a bit complicated, but here's a good example to see what I mean, to show you what I mean. So let's do some key stuff here. So the question is, f of z equals, let's just say, f of z equals z squared, and gamma of t equals t squared plus it. And t is an element of the closed interval between 0 and 1. Okay? So now, let's plug all of this into our formula. The integral along the smooth path gamma of f equals, well, a is just 0 and b is 1. Okay? So it's the integral between 0 and 1 of, well, okay, so f of gamma of t. So gamma of t is t squared plus it, but then f of z is just z squared. So it's the whole thing squared, okay? But we're not done. We have to multiply by the derivative of gamma of t. Well, the derivative of t squared plus it, that's pretty easy. Power rule, bring this down here, subtract 1, plus, well, the derivative of c times t is just c, so in the end we get 2t plus I dt. Okay? Now, expanding this term here, leaves us with the integral between 1 and 0 of t squared squared is just t to the power 4, plus 2 times t squared times it, so 2I, and then the t squared and the t, we can combine the powers to make t cubed, minus t squared, yeah, because it squared is I squared times t squared, which is negative t squared, because I squared is negative 1. So in the end we get minus t squared, and then that times 2t plus I. And here's the second theorem, which I promise, well, it's more of a lemma, But here's the second thing. I promise I'll prove this and this in maybe the same video or 2 different videos. But if and only if we hit 5 likes. Okay, anyway, back to the video. We can split this up to make it a lot easier for ourselves. This actually equals the integral between... This actually equals the integral between 0 and 1 of 2t to the power 5 minus 4t cubed dt plus I times the integral 5t to the power 4 minus t squared dt. And I'll show you where this comes from only if we hit 5 likes. Now, this is quite easy. Just use the power rule a few times and then evaluate at the bounds. So, add 1 and then divide by the new power. So, 2 over 6 equals 1 over 3. T to the power of 5 plus 1, which is 6. Minus, well, add 1, divide by 4. That cancel. So we get we get t to the power of 4. Evaluated at the bounds, 0 and 1. Plus I times, and now we have to evaluate this integral. Well, plus 1 over 5. Boom, boom, that and that cancel. Anyway, yeah, boom, boom, that cancel. So we get t to the power of 5 minus plus 1 over 3. So we get minus 1/3 t cubed. Evaluated the bounds, 0 and 1. And now we're very nearly done. So, here, when we plug in 1, we get, because t is our variable, we plug in the 1s into our t, we get 1/3 times 1 to the power of 6, which is just 1. So we get 1/3 minus t to the power of 4, which is just 1. So minus 1, which equals 2 over 3. That equals negative 2 over 3. Okay? But then when we plug in 0 into this t, that part vanishes. And when we plug in 0 into this t, that part also vanishes. So we get 0 minus 0, which is just 0. So the first bit is negative 2 over 3. Then plus I times, plug in 1, we get 1 minus, 1/3 times, 1 cubed is just 1, so minus 1/3. Okay? And then this times I. And then minus, when we plug in 0, we get 0. And then minus 1/3 times 0, which is just 0. So I times 0 minus 0, which equals 2/3 I. And this bit will go away. Which means after all that nice little work, which I will prove more rigorously if we get 5 likes, we get negative 2/3 plus 2/3 I. Thank you guys for watching. I will be starting a series on complex analysis, and hopefully that's interesting for you. Hope you enjoyed the video. Goodbye.